Good morning. Welcome to this session of your course, Logic Design and Switching Circuits, Logic Design and Digital Circuits for the other department, I think. Just to test audio, am I audible? And can you see my screen?
Yes, sir.
Right. Last time we met, we discussed, I introduced Boolean Algebra, a bit all over the place. But here we are today. I introduced Boolean Algebra definition as a set of rules used to mainly minimizing circuits. We talked of need for analysis and design of circuits. How do you approach building a circuit? You are provided with a problem and you need a solution for it. How do you come up with a solution? There is need for analysis. There is need for design. We answered the question why Boolean algebra, why we have those set of rules. And basically, this is to have the best circuit as possible. I think I gave a quite a number of examples where you have one problem but with many solutions. One problem, many solutions. How do you see if a solution is the best? That's why we have Boolean algebra to identify the best circuit or the best solution for a problem based on the size of the circuit, the power, and the performance of the circuit. We mentioned quite a number of rules which you need to either claim or much better understand with I think the most interesting one being the De Morgan's theorem. You really need to get this one because I think most of the questions, sadly, if I can say, most of the questions in the exam will probably require your knowledge of the De Morgan's theorem. Sadly, because A plus B, no. Everything you're learning, it shouldn't be for the exam, though. It should never be about the exam. It should be about understanding, preparing yourself for the industry, preparing yourself to be an engineer. Unfortunately, it involves exams. So you have to balance between your understanding and expressing yourself in the exam. Right, we talked of universal gates, a bit all over the place as well. But I'm hoping you get a thing or two, how if we are given a circuit with the primary gates, the ends, the ors, the nodes, how you can convert that circuit to only use universal gates. We have two types of universal gates, the NAND and the NOR. How can you convert a given circuit to only use those two type of logic gates? You need to understand how to do that. I tried the best I could to explain. I'm hoping you can add a little beef on that skeleton and find yourself getting distinctions. Right. We talked of the why part, why universal gates. It's really important to understand why. Questions, why are we doing this? I think that's a very important question to answer. And I'll be emphasizing on that for each and every course. I do, because if you don't understand why you are here to begin, then there are issues. In logic design, if you don't understand why we use Boolean algebra, why we have logic design in the first place, in this case, why we have universal gates, then you have issues. So you need to understand why and learn to ask those questions. The why part, we have advantages of why we use the universal gates. Faster switching, they are relatively cheaper and easier to build a circuit with. When we build ICs, instead of using all the primary gates, the different types of primary gates, when building your ICs, your chips, it will be easier to use only the universal gate. Now, we also finish the sessions with Boolean functions. With Boolean functions, we mentioned a Boolean function f being represented by either an expression, where there you go. Be very careful. Be very careful with your mutes with that. Mavis. Be very careful. All right. I mentioned functions. We ended the session with functions, and I mentioned functions being represented by either an expression or a truth table. You need to learn how to build these truth tables. 0, 0. What is F? Participation. We have a truth table there. We have an expression. Help me fill that truth table, please. What is F? Participate. Lesson is officially begin. Participate. What is F?
They were using which gate?
I'm using which?
Gate.
Gate. I have an expression there. I have an expression there, and I'm 0, 1, 0, 0.
A bar and B.
A bar B. So this is 0, this is 0, this is 0, this is 1. We just got an answer from, who is that? From the chat. Yeah, unfortunately, I can no longer identify who gave us that answer. Okay, chat. Taona Rotida, thank you very much for picking that up quick. Everyone should be able to do this by this time. A function f can either be represented by a logic, an expression, a truth table, or by a logic diagram. A logic diagram with a bar and B. So here we have A bar, B. 3 ways which you can represent a Boolean function f. You need to understand these 3 ways, how you can go from way A, B, C, and vice versa. All right. So that is what we ended up doing the last time we met. And today we'll be talking of min terms, max terms, sum of products, product of sums. We call this canonical forms. Today we'll be talking of canonical forms. Right, just a minute. Okay. Canonical forms. What are these? For every function f, it has 2 forms which we can represent it. Each function, it has 2 forms in which we can represent it, and these are called the canonical forms. We have the sum of product SOP. We have the product of sum POS. Two forms. These are the two canonical forms. All right, quick example. The function I just gave you, a bar b, this is an SOP function. Why? Because it has product on it. Maybe not sum, but it has product on it. A much clearer example is another function, a bar b plus a b c. Now, this is a perfect example for a sum of product canonical form. What we mean by that, we have sum of products. Sum of products. An example for product of sum. An example for the product of sum canonical form, we have a bar plus b. We have a plus b plus c. We have product of sum. There is a difference there. And I'm hoping someone sees the difference between those two. We have sum of products, sum of these products, A, B, C, that's the product. Here we have product of sums. We have the sums A plus B plus C and product of those sums. Those are the two canonical forms which helps in a representation of functions. So when you talk of Boolean algebra, we have two forms of representation, SOP and POS. Right. With these SOPs and POS comes what we call min terms and what we call max and what we call max. Nyasha Neshumba, be very careful. We have what we call, where are we in Africa? Here we are. Okay. So we have SOP here, we have POS here. An example. I just gave an example, AB plus ABC. We have A bar plus B, A plus B plus C. I don't think these two functions are the same though, even if they have maybe similar variables, but they are not the same. I'm just giving examples. Right, I was mentioning min terms. When we talk of sum of products, we have what we call min terms. When we talk of POS, we have what we call max terms. What are min terms? What are max terms? Boolean algebra can appear in the normal X or X bar form. Right, background. A Boolean variable, it can either be X or X naught. A Boolean algebra, it can either be 1 or 0. It can either be 1 bar, which is equal to 0. It can either be 1, excuse me, it can either be 1 or 1 bar, which is equal to 0. A variable can take two forms. A min term is a variable complemented if its value is 0. Otherwise, it is uncomplemented. A variable is a complemented, a min term is a variable which is complemented if its value is 0. So definition of a min term. If its value is 0, then it is complemented. When you talk of complement, we talk of this bar. It is complemented. If its value is 1, it remains uncomplemented. So if you have a 0, it becomes an x bar. You are given a variable x. If it is 0, it becomes x bar. If it is 1, it remains uncomplemented. These are the min terms. Now for the max terms, a variable is complemented if it's 1. So for max terms, if your variable is 1, then it's complemented. If it's 0, it remains uncomplemented. Definition of these two canonical forms can also be given in terms of min terms and the max terms. So here we have sum of min terms. Here we have sum of max terms. So what do these variables represent? A bar. A bar, it means it's the same as x bar, it means the same as 0. These are the min terms. So here we have a 0. B, this is not complemented, so it's a 1 wherever it came from. Here, all these A, B, C, they are all uncomplimented. It means these are 1s. Right. For POS, it means here we have A bar, which is X bar. So this is a 1, this is a 0, uncomplimented, 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 uncomplimented. With practice, you understand these complemented, uncomplimented confusion. Right, another example. Each end combination of terms is a min term. Each or combination of max terms is a max term. So this combination of end, this is a combination of A bar and B. This is a min term. We have another combination of ends here, A and B and C. We have another min term here. We have 2 min terms. So it means here we also have 2 max terms, which each or combination of terms is a max term. Each or, here we have A bar or B. Here we have A or B or C. So each product, each end combination is a min term. Each end combination is a min term. Each or combination is a max term. Right. You probably get a better understanding when you get into the examples. And with that, I bring in an example. Which we can deal with. All right, we have a function G. Where are we in Africa? Okay. We have a function G, which is equal to M367. All right. That is a shorthand notation for a function. And you will be using it frequently. That is a shorthand notation for a function. What does it mean? G is equal to x, y, z, 1, 2, 3, plus x, y, z, plus x, y, z. 3, just a minute. Let me first give you the answer, then I make explanations going towards the 7. Right. This is the same. 2 different notations for the same function. How do you go from this to this? So what we have here, we have a summation. It means sum of, we have a small m, mean terms. Sum of mean terms. Which mean terms? Which mean terms? Mean term number 3, mean term number 6, mean term number 7. So if I have 3 variables x, y, z, 0, 1, 0, 1, 0, 1, it means I have 8 possible outputs: 1, 2, 3, 4, 5, 6, 0, 1, 0, 0, 1, 1, 0, 0, 1, 1, 1, 2, 3, 4. 1, 2, 3, 4. It means I have 8 possible outputs. This is mean term number 1, mean term number 2, nope. Mean term 0, if I can put it like this. Mean term 1, mean term 0, mean term 1, mean term 2, 3, 4, 5, 6, 7. The 7 representing this 1, 1, 1. If I can use the formula I gave you to find the variables, so this is 0, this is 1, 2, 4. If we have a 1, 1, 1, it means it's a 4 plus 2 plus 1, that's a 7. So we have min term 0, 2, min term 7 for 3 variables. For 3 variables, I have min term 0, 2, min term 7. Going back to the notation says it's a sum of min terms, sum of min terms number 3, number 6, and number 7. Min term number 3. What is min term number 3? It means G is equals to sum of the min terms. Min term number 3 is this one. It's 0, 1, 1. If I can start with 0, 1, 1, this is min term number 3. Sum plus number 6 is 1, 1, 0 plus number 7 is 1, 1, 1. Sum of the min terms. Now putting it into proper into a proper expression, what is a 0? When we talk of midterms, what is a 0? When we talk of midterms, a 0 comes in its complemented form. A 1 remains uncomplemented. So each 0 is complemented. So here, if we had the variables x, y, z, it means this is x bar y z plus x, y, z bar plus x, y, z, which is the same as how we got here. So I can give you a question. The question will not start with the expression we already introduced. The question will start with this kind of notation. I will still need answers, and it's up to you to have seen this video and understood how we came about getting from the notation to the expression. So we have our function g, which is the sum of min terms 6, 7. G is x, y, z plus x, y, z plus x, y, z. There's a z bar here. Yes, the same. This is an example of sum of products. This is an example of sum of products. G can also be represented in, so this is sum of products. G can also be represented in the canonical form product of sum. Product of sum. How do we do that? I'll start with the expression G is equals to sum. That is the symbol for sum of max terms. What max terms? We now have 0, 1, 2, 4, 5. Where are these numbers coming from? These numbers are coming from here. So this is my M0. Where are we in Africa? This is my M0, M1, M7. When I have a function, running out of time, when I have a function like this, my function is G. Right, my function G. When I have the function G, where it came from? It came from here, the sum of products, 3, 6, 7. What it means, at M3, the function, it has an output of 1. 0, 1, 2, 3. There is a 1 here, 4, 5, 6. There is a 1 here. There is a 1 here. That is basically what it means. If you have a function given in this notation, it means for the mean term number 3, the mean term number 6, and the mean term number 7, the output is 1 from the perspective of sum of products. Now, from the perspective of product of sum, it means the output is 0. Where the output is 0, that's where we'll be dealing with for how do I move this? Can I copy this? Okay, I cannot move it. From a perspective of product of sum, I just explained where we got from the SOP. Now from the perspective of POS, we're now dealing with outputs 0. When we deal with output 0, it means my function G is equals to product of max terms. Where the output is 0, it's M1, output is 0 here. M2, output 0. M3, output 0. No, this is M0. M1, M2, 0, 0. This is M3, M4, M5. These give us the output 0. So we have 0, 1, 2, 4, 5. Notation, then representation is an expression. We now have sum of max terms. What is max term number 0? Max term number 0 is x plus y plus z. Now to the complements and the uncomplemented factors, if it's a 1, it means it's an x bar. If it's a 0, it's an x. So here we have 3 zeros. So they remain uncomplemented. So we have x plus y plus z. Product of sums. For 1, we have 0, 0, 1. If I can put it like this, I think for the sake of understanding. So for 0, we have G is equals to 0 product 1, this is 1, product 2, product 4, 0, 1, 2, 3, 4. 1, 0, 0, product 5. Proper expression for a 0, it is not complemented. From the definitions of our max terms, if it's a 0, it's not complemented. If it's a 1, it is complemented. So here we have x plus y plus z. Next one, we have x plus y plus z bar, because we have a 1 here. We have x plus y bar plus z. We also have a product of x, y, z. We have a 1 here, we have a 1 here. Different types of forms representing these factors. So here we are. We have G.
Sir,
Yes.
hatina kuita ya 100.
Taita H.
Taita ya 101 tajambira the one before that.
Explain
Which is
exactly where we are and what you mean.
I mean like between 010 and 101 tasira expression ya 100 which is x bar plus y plus z. By expression, say.
Okay, by expression. So we
Yes.
have 0, which is 0, 0, correct? 0, 0, 1, correct? 0, 1, 0, correct? 1, 0, 0, correct?
100.
1, 0, 0 is 4. It's correct. There's a 0 there. 1, 0, 1 is a 5. Is correct. So this is 0, 0. This is 0, 0, 1. This is 0, 1, 0.
So 100
voila.
is not there.
We can as well just do this. Thank you very much. So this is x bar plus y plus z. Thank you very much. I really appreciate it. It means someone is listening out there. There we are. We have our product of sums. Two types of representations. So it means an expression G can be equal to what's this? 0. Oh, yeah. Sum of 3, 6, 7. 3, 6, 7, which is equal to xyz plus xyz plus xyz 1, 2, 3. So this is x bar, z bar, and this. This is sum of products. The same G can also be represented using the product of max terms. It will be 0, 1, 2, 3, 4, 5, 6, 7, which is equal to all the 5 we just did here. Where are they? Here. Two forms of representing. This G here is the same as this G here, is the same as G here. They are all the same, but with two forms of representation. As you can see, I think you will note that this is much simpler, I think. This is much simpler. Instead of using the one with the x plus y plus z, etc. So that's an example of how we can represent a Boolean function using the two forms, sum of products and product of sum. So provided you have a table, you can come up with an expression for the sum of products. How do you come up with that expression? You identify your ones. Your ones becomes your min terms. So this is min term number 0, 1, 2, 3. Min term number 4, 5, 6. This is min term number 7. You identify your min terms and you sum them. If you want to go the product of some way, you identify your max terms. Your max terms, they have the 0 output. So you have M0 less than 1 minute, M1 M4, M6, M5. Right. We continue after exactly 5 minutes. 11:45. We continue the session from where we just left off because our 40-minute limit is up. Join me.